Welcome to Summarize Science, where we break down fascinating new research. Imagine the moon's gravity pulling on Earth's oceans, creating tides. This stretching effect happens to all celestial bodies, and scientists have a measure for this squishiness, called the Tidal Love Number. According to Albert Einstein's theory of general relativity, black holes should be perfectly rigid. In other words, they should have a tidal love number of 0. They have no love for being tidally deformed. Testing this prediction is a huge deal because finding a non-zero squishiness would mean our understanding of gravity or black holes is incomplete. It could point to exotic new physics or that the objects we think are black holes are actually something else entirely. Recently, scientists got the perfect opportunity to run this test using an event called GW 250114. This was an incredibly clear and strong gravitational wave signal from two merging black holes. The signal was so pristine that it allowed for the most precise measurements of its kind to date. Researchers carefully analyzed the ripples in spacetime from this merger, looking for the telltale signature of tidal squeezing. So, what did they find? Their analysis, shown in this graph, reveals that the data strongly prefers a tidal love number of 0. The black holes behaved exactly as Einstein's theory predicted, showing no measurable deformation. This allowed the researchers to set the tightest constraints ever on the squishiness of black holes. This null result has some profound implications. First, it rules out certain alternative models for these compact objects. For example, some theories propose the existence of boson stars, which are exotic objects that would have a non-zero tidal love number. As you can see in this chart, the results from this study rule out several models of boson stars, shown here in the shaded regions. This means it's highly unlikely that GW 250114 was a merger of these specific types of exotic stars. Second, the findings place strict limits on any environment that might be surrounding the black holes. If there were a dense cloud of dark matter or an accretion disk around them, it would make the system appear squishy. The data shows that any such environment must contribute less than about 0.7% of the black hole's mass. So, to recap the key points from this incredible study, an exceptionally clear gravitational wave signal was used to perform a high-precision test of Einstein's theory. The results confirm that black holes are not squishy, just as general relativity predicts. This provides the strongest evidence yet for vanishing tidal love numbers in black holes. And finally, these findings rule out some exotic alternatives to black holes and severely constrain the environments they live in. This work showcases how gravitational wave astronomy is evolving into a tool for precision science. It's allowing us to probe the most extreme corners of the universe and test the very foundations of physics.